Another way to think about differentiation is that it's the inverse of integration. So differentiation is the inverse of integration. So if I were taking the derivative with respect to x of the integral of f of x dx, then these two operations cancel each other out, and I'm just left with the function f of x itself. We can start to formalize the rules of integration. For example, if we know that the derivative with respect to x of a constant is 0, then the integral of a constant c with respect to x is, the integral of 0 with respect to x is going to be a constant. We also know that the derivative of some constant k times x is equal to k. And so if we wanted to go in the other direction, if we were integrating k dx, then we get k times x plus the constant of integration. Similarly, when we differentiate kx squared, we get 2kx. And so if I were integrating 2kx dx, we get, well, I can pull the 2k out, that's a constant, and so I'm really just integrating x dx. So integrating x with respect to x. And so I have 2k times x squared over 2 plus this constant of integration. And if I simplify that, the 2's cancel. There we go, 2's cancel. And so I'm left with kx squared plus c. If we continue to increase the power terms, we'll see a pattern starting to emerge. So for example, the derivative of kx cubed is 3 times kx squared. So if I want to go in the other direction, then I would be integrating 3kx squared dx. And again, I can pull the constant out side of that integrator term. And so I'm left with x squared dx. And so when we integrate x squared, I have x cubed over 3 plus the constant of integration. And I have to remember to keep this 3k. So again, the 3's will cancel. And so we have k x cubed plus c. So above, we were integrating x dx, and we ended up with, well, we're trying to get back to kx squared, and so we end up with kx squared plus c. Here we were integrating x squared dx, and we get x cubed plus c. We have that constant in there to keep track of. So let's look at one more. So we're going to differentiate with respect to x, kx to the 4th. And so this gives us 4kx cubed. And so if I want to go in the other direction, and if I were integrating 4kx cubed dx, I can take the 4k outside of the integral, and now I'm just integrating x cubed dx. And so we have 4k times x to the 4th over 4 plus this constant of integration. Again, the 4's cancel, and so we have k x to the 4th plus c. And so we should be able to see this pattern emerging where we started with, let's see, we were integrating x dx, and we get x squared plus c. We switch here. There we go. Scroll down. All right, so we were integrating x squared. We end up with x cubed plus c. We were integrating x cubed. We end up with x to the fourth plus c. And so we can actually generalize this process. So if we were differentiating, this is like our power rule for differentiation, x to the nth power, we multiply by n, and then reduce the power by 1. So we end up with nx raised to the n minus 1. So if I were integrating, if I go in the other direction, but I'm starting with x to the n, so I'm integrating x to the n dx. The process is a little bit different. We have x to the n plus 1 divided by n plus 1, n plus 1, plus our constant of integration. And this is valid for all values of n, except we can't have a 0 in the denominator. So that means that n cannot equal negative 1. And later on we'll explore another method to deal with that case. But this is our general power rule for integration. And we have some other general rules that we can review. So hopefully it's apparent at this point. If we are multiplying some function by a constant k and differentiating with respect to x, then that constant k gets carried through, and we end up with the derivative f prime of x. And the same is true when we're integrating. So if I'm integrating k f of x dx, then as we said before, that k can get pulled outside the integral, and it's the same as just multiplying k times the integral. So, all right, so that's our constant, dealing with the constant multiplier. Let's review some other rules quickly. Here we have some other rules for integrating. So if I'm integrating f of x, and I could be adding or subtracting some other function, g of x, and I'm integrating both of those functions with respect to x, this is the same as integrating f of x dx and then adding or subtracting the integral g of x dx. We also have some rules for trigonometric functions. So for example, the integral of the cosine of x with respect to x is sine of x plus the constant of integration c. If we integrate sine of x dx, we end up with minus cosine x plus c, our constant of integration.